Yeah, good afternoon to one and all present here. Hope you all safe and healthy even in this pandemic situation. On behalf of ISI Bangalore students, I would like to welcome all the participants to the first day of Mathematics Online Camp of Limit. So, this lecture will be delivered by Pranav Krishna. He is currently pursuing his BMath and in his third year of his academic course. His main field of interest is analysis, and we are going to hear from him on the topic numbers, real and otherwise. So, Pranavda will speak for about 1 hour, and then at the end, we will open up for the questions for about 20 minutes. And please do type your questions in the main chat box. We will find all the questions and ask him one by one. And you are requested to keep yourself mute until asked by the speaker. Okay, over to you, Pranavda.
Yeah, the plan is to construct N, Z, Q, R, and C, and then we'll talk about p-adics. The essence of N is captured by Peano's axioms, that is, 0 belongs to N, and the next we talk about equality being an equivalence relation, that is, equality is reflexive, symmetric, and transitive. Then we have that equality is closed over natural numbers, that is, for all elements A and B, if B belongs to N and A is equal to B, then A belongs to N. Then we define the successor function. We assume the existence of a successor function. That is, for every natural number, its successor is also a natural number. Then we have that for all every m and n natural numbers, m is equal to n is equivalent to saying the successor of m is equal to the successor of n. Then we have the seventh axiom, that is 0 does not have a predecessor. That is, for every natural number, s of n is not equal to 0. The last axiom is about induction. That is, if there exists a set K such that 0 belongs to it, and for every natural number, its successor belongs to it, then K is equal to the natural numbers. Now we're going to construct N. Firstly, assume that there exists a set, call it phi. Construct another set with phi as its only element. That is this set over here. Phi is the only element of this set, and now repeat. Let n is the set of all such subsets, and S from n to n denote the operation of putting a set into another set as the only element. Note that this n is black and this does not have the second bar that we have over here. This is supposed to denote that n might or might not turn out to be the natural number. We'll have to show that it is. So first talking about the first axiom, which holds true because we have assumed that there exists a set and called it phi, and phi belongs to the natural numbers. The second, third A and third B are all true because of the axioms of set theory. And similarly, the fourth one. The fifth one is about the successor of n, which clearly holds true because for every set you can put it into another set as its only element, thus the successor exists. For the sixth one, m is equal to n by implies s of m is equal to s of n. This also holds true by set theory. Basically, we peel out layers of the onion, that is, the onion which has phi at its core. The seventh one holds true because the operation involves putting a set into another set, and we have assumed that phi is the seed, the beginning, so there is nothing. And the ninth one also holds true. Clearly, n comma s satisfy the Peano axioms, that is, all hold valid. Thus, we have constructed natural numbers. There are other constructions of n, but this is good enough for us. Now we're going to construct z from n. Now for all pairs a comma b and c comma d belong to n squared, we define a relation a comma b is related to c comma d if a plus d is equal to the b plus c. That is, the outside elements have the same sum as the inside elements. It is easy to see that tilde is reflexive, symmetric, and transitive. we're going to prove transitivity over here. Say A comma B is related to C comma D and C comma D is related to E comma F. That is A plus D is equal to B plus C and C plus F is equal to D plus E. We're going to sum the two equations and cancel out the common elements to get A plus F is equal to B plus E. Thus we get that A comma B is related to C, E comma F. That is, tilde is transitive. Now we're going to define Z as the set of equivalence classes of n cross n modulo tilde. A few examples over here now. Suppose we find out all the elements m comma n that in n squared that are in the same equivalence class as 1 comma 1. That would mean m plus 1 is equal to n plus 1. That is m is equal to n. Thus n comma n is related to 1 comma 1 for all n. Suppose we want to find out all elements that are in the same equivalence class as 0 comma 27. That would mean 0 plus n is equal to m plus 27. This means 0 comma 27 is related to n comma m plus 27 for all n. It looks like a comma b denotes a minus b in some manner as 0 comma minus 27. 0 minus 27, this comma appears to be a mistake, is equal to m minus m plus 27 for all n. Now we're going to define addition over z. So plus is a binary operation from z squared to z such that the equivalence class containing m comma n and m prime comma n prime goes to this equivalence class. We show that plus is well defined. Suppose m comma n is in the same equivalence class as m prime comma n prime and a comma b is in the same equivalence class as a prime comma b prime. That is m plus n prime is equal to m prime plus n and a plus b prime is equal to a prime plus b. Then m comma n plus a comma b is defined to be m plus a and n plus b, and m prime comma n prime plus a prime comma b prime is defined to be m prime plus a prime and n prime comma b prime. Just summing up the first corresponding elements, the first one and the second one. Makes sense. Now recall that these two are in the same equivalence class and so are these two. So m plus n prime plus a plus b prime is equal to m prime plus n plus a prime plus b. Regrouping the terms, we get that m plus a plus n prime plus b prime is equal to m prime plus a prime plus n plus b. That is m plus a plus n prime plus b prime is equal to n plus b plus m prime plus a prime. Thus the operation is well defined. Now we're going to prove commutativity for plus. Say m comma n is added to a comma b. Note that all these are equivalence classes. These don't denote particular elements of n squared. These are the equivalence of classes of n cross n modulo tilde. The equivalence class containing m comma n plus the equivalence class containing a comma b goes to this thing over here. And we want to find out if a comma b plus m comma n is equal to m comma n plus a comma b. A comma b plus m comma n is equal to a plus m comma b plus n, which commutes because these are natural numbers, m plus a comma n plus b, and now we will come out and show that plus is commutative. We still need to define multiplication on z. Define multiplication on z as a binary operation on z squared to z as m comma n and m prime comma n prime going to mm prime plus nn prime and mn prime plus nm prime. That is a bizarre definition indeed. Why would someone define it this way? Recall that m comma n essentially denotes m minus n. Thus m comma n star a comma b should denote m minus n times a minus b. That is ma minus mb minus na plus nb. We sort out the terms to make that happen. ma plus nb minus mb plus na. which is exactly what happened over here. I hope everybody is convinced. Now we'll show that multiplication distributes over addition and z. Over m comma n times a comma b plus c comma d is equal to m comma n times a plus c and b plus d, which becomes the product of the first one, the product of the second one, that is ma plus mc plus nb plus nd, the outside product and the inside product, mb plus md plus na plus nc. Now the distributed part over here is m comma n times a comma b plus m comma n times c comma d, which evaluates to ma plus nb comma mb plus na, the outside and the inside. Added to the outside product, the corresponding product mc plus nd, comma the outside product md plus the inside product nc. Summing these two, we get ma plus mc plus nd plus nb, comma mb plus na plus md Hello? Is everybody there?
Yeah, yeah.
Yeah, okay.
I thought it stopped. Okay. Now we're going to construct Q from Z. Similar to the construction of Z from N, we're going to define the set Q cross Q and the relation tilde that gives us Q. Let A comma B and C comma D are pairs in Z cross there, and A comma B is related to C comma D if AD is equal to BC. Note that if two rational numbers P by Q and P1 by Q1 are equal, then PQ1 is equal to P1Q. The relation represents this relation, that is, represents cancelling out a common factor from the numerator and denominator if rational numbers exist. We're going to define the right set S. S is the pair of natural numbers, what do you call it? Integers A comma B such that A comma B belong to Z and B is not equal to 0. And define A comma B is related to C comma D if AD is equal to BC. It is easy to see that tilde is an equivalence relation. Then Q is defined to be the set of equivalence classes of S modulo tilde with addition defined in the corresponding manner. A comma B comma C comma D goes to AD plus BC comma BD, and multiplication defined in an easy manner. A comma B comma C comma D goes to AC comma BD. We will show associativity for plus and Q squared. So A plus B plus C plus A comma B plus C comma D whole added to E comma F is equal to AD plus BC comma BD plus E comma F, which evaluates to FAD plus FBC plus BDE comma BDF. Now we're going to evaluate the other term, that is A comma B plus C comma D plus E comma F, which evaluates to CF plus DE and DF, the denominator, and which evaluates to ADF plus BDE plus BCF and BDF. Note that these two are the same, and thus plus is associative and Q squared. Now we're going to construct R from Q. So everyone knows that root 2 A is equal to 1.414 and something and all. Here I have a list 1, 1.4, 1.41, 1.414, 1.4142 and something. And this is getting progressively closer to root 2 and we are heading one more right decimal place at every step. A few definitions now. A sequence of rational numbers is a function from n to q denoted as this n equal 1 to infinity a n, where a n denotes the function evaluated at the natural number n. The important idea about constructing is we are concerned only with what happens towards the tail of the sequence, what is called the tail behavior. So this sequence that x1 is equal to 10 crore, x2 is equal to minus 5, x3 is equal to 0, and x4 is equal to 1 can also approximate root 2, as getting another digit correct in the decimal expansion of root 2 is not necessary at every step. The fact that I told you that this sequence goes to root 2 is enough. Another example of a sequence is xn is equal to 1 over n. Now, a definition of a Cauchy sequence. A sequence is called Cauchy if the terms of the sequence become closer and closer in this particular way. That is, for all natural numbers, there exists another natural number n away, such that for all m and n more than n away, xn minus xm is less than 1 over a. As a goes on increasing, the n of a might also go on increasing or whatever it might do. We just want that xn minus xm should be less than a for all m and n more than n away. Remark. The terms of the sequence are getting closer and closer together, but they must also be coming closer and closer to something, right? This is not true in Q, as root 2 does not belong to Q. Now I'd like you to see a sequence. So as you can see in this video, all the runners are becoming closer and closer to the finish line, but this one does not actually reach it. I mean, they reach the finish line, they don't actually reach the hoarding. They, in some kind of way, fall under it. Yeah. Another definition, a sequence xn is said to converge to T if for all a positive, that is a natural numbers, there exists n away such that for all n greater than n away, xn minus t is less than 1 over a. This is denoted as sequence xn going to a. Yeah, this is denoted as this and this is read as xn goes to 1 over a. Now we're going to define the right set. CQ is the set of all Cauchy sequences in Q. And tilde is an equivalence relation on CQ where xn is the sequence xn is related to the sequence yn if xn minus yn, which is another sequence, goes to 0. It is easy to see that tilde is an equivalence relation and we're going to define plus and on R square to R. Plus behaves as one would expect it to behave, that the terms of the sequence add term-wise, and so does multiplication. It is possible to show the density of Q in R and various other properties, but they aren't the right things to do after 10 minutes to do 10 minutes after learning about sequences. Now we are going to construct C from R. C is the set of A plus Bi where A comma B are real numbers, where addition and multiplication work as one expects them to. Yeah. Another remark. One might feel that the construction of R from Q is qualitatively different from all other cases, especially because it needed the notions of convergence, Cauchy sequences, and more importantly, the notion of a sequence. Using sequences to fill in gaps like we did in Q is called completion. Then we say that R is a completion of Q. So now we're going to the part where we talk about p-adics. Ways of thinking about R. R is the completion of Q. R can be thought of as the numbers that go on endlessly to the right of the decimal. Or we can think about it as the set of all infinite, what do we call them, polynomials with I equals z not to infinity, z It is bi 1 over 10 to the I, where z naught belongs to z and bi belongs to 0 to 9. That is, bi is one of the single digit natural numbers or 0, with plus and dot defined by the usual operations involving carryover and borrowing. But what happens if one replaces 1 by 10 with something like 2 or 3 in the definition? We get the p-adics. QP is defined in a similar manner. I equals z naught to infinity summation bi p to the I, where z naught belongs to z, pi belongs to the set 0 to p minus 1, and p has to be a prime. It is not clear why p has to be a prime, but I will show that later. Addition and subtraction and multiplication in QP are similar to those in R square. That is, we go from the right to the left, matching powers, and carry over or borrow if needed. For example, in Q2, will someone like to tell me what this element evaluates to in Q2? This one, yeah. Yeah. I hope someone will speak up. Call up people.
Yeah, you can raise your hand and then uh,
You can just unmute yourself and ask.
Yeah. Oh, someone is supposed to tell me what this represents in Q2. This is 2 to the 0, this is the coefficient of 2 to the 1, this is the coefficient of 2 to the 2, and all others are 0.
5.
Yeah, exactly, this is 5. And what about this one? Over here.
3.
Yeah, good. So adding it, what do you get adding 1 to 1 in Q2? Oh, come on, keep answering.
0.
So it will be 1000.
Yeah, 0 and 1 carries over, right?
Yes.
Yeah, then we're going to add the second term, 0 plus 1, and this one over here. What does this evaluate?
0
1,
again.
Yeah, good.
0, carry 1.
Carry 1 again. I won't write that again. This should work. What do you have next? 1, 0, and another 1 over here. This should evaluate to?
1, 0.
Okay, good. Oh, I shouldn't write the 1. This is 10, and there is a 1 carryover again. And all other terms are 0 in both these numbers. So we write the number 1 over here. See, it is similar to doing multiplication, addition, and everything in base 10. So will someone like to tell me what does this evaluate to?
8.
Yeah, so what we did was 5 plus 3 is equal to 8. Yeah, makes sense. In Q2 itself, this particular element that I equals 0 to infinity 1 times 2 to the, oh god, 2 to the I belongs to Q2. What if we add this element which contains 0 at every place except the last one? What if we add it to it? This is the element A that we defined over here, and this is the element that contains 1 at the last place and 0 everywhere else. What happens over? 1 plus 1 becomes 10, 1 goes for carryover, 1 plus 1 becomes 10, and 1 goes for carryover, and this goes on, and consider any arbitrary term that is not at the end. 1 plus 1 goes to 10, and 1 carries over. 1 comma 1 becomes 10, 1 carries over, and so on and on. So the sum of these two elements, A and this particular element, is 0. That is, if we are in Q2, we get to write 1 plus 2 squared plus 2 cubed and so on, evaluates to 1 over 1 minus 2, which is equal to minus 1, and it is perfectly fine because we decided it was.
Pranav, once
Uh-huh.
1 minute. Someone raised his or her hand. So
Okay. Would they please speak
Yeah,
up?
unmute yourself and
Ah,
say.
I guess
is
it was by
everything okay?
mistake, I think. I
Okay,
guess
Yeah,
it
it
was
might
by
be a
mistake.
mistake. No
You
harm.
can continue.
yeah, okay. You can continue.
Good enough. So we just showed that 1 plus 2 and 2 square and 2 cube, one can decide to add them and it might evaluate to -1 and it would be perfectly fine. Suppose we had an element A belongs to QP, which is A is equal to summation BIP to the Ri, and one might ask what would be the representation of -A. Recall that one of the ways to subtract any two-digit number from 100 is to use 10 minus the ones digit and 9 minus the tens digit. For example, to subtract 11 from 100, one might do 10 minus 1 is equal to 9 for the units digit, and 9 minus 1, which is 8, the tens digit, and it would be right. 89 plus 11 is equal to 100. Similarly, in QP, we subtract the last digit from P and all others from P minus 1 to get the complement of A, the additive complement that is. But it is not clear that we need P to be prime. Division makes it so. So a small example of division in R, the usual division, we decide to divide 2 by 7. 7 does not go into 2, so we put a 0 over here and copy down a 0 over here. This becomes 20. 7 times 2 is 14. 20 minus 14 is 6, and this is 6 over here. Copy down a 0 over here. 7 times 8 is 56. This becomes 4. Copy down a 0, and so on and on. And note that we have a 20 over here and a 20 over here, so they should start repeating after this. The way to interpret this is, if 2 by 7 is this particular sum, then 2 is equal to 7 times the sum. Similarly, in Q7, what would be 1 over 3? Just like our case above, we decide to check out multiples. Thus, we first check that we first check that 7 does not go into 2. We won't be doing that over here. It actually turns out that all rational numbers in Q become integers in QP in a manner of speaking, but I won't be proving that or covering over here, but you should know that. Okay.
Pranav,
Uh-huh.
yeah, Ayon has raised his hand. Ayon, can you please unmute yourself and ask the question?
Sir, can you please repeat how summation 2 power I evaluates to -1? This was a
Okay,
long time ago.
I can talk about that. Yeah. So consider the last term, that is 1 plus 1. What does this evaluate to? As people told over here, it
0.
evaluates to
Yes.
10 and the 1
10.
goes carry over, right?
Yes.
And if you consider any other term except the terminal ones, what do you expect? There's a 1 from carryover from the other place, the one at the right of it, and there's a 1 over there. What does that evaluate to? Again, it evaluates to 10,
10.
right? And that holds true for every non-terminal place, that is, right?
Yes, it holds.
Yeah. And there are only two kinds of places in a number, right? The terminal place and the non-terminal place,
Yes.
right?
Yeah.
So what happened over here is that every place in the number evaluated to 0. Is it true or not?
It is true.
Yeah.
It is
And
evaluated to 0.
the way we define R, what happens if this pi is equal to 0 for every I? It is the number 0.
It's the number 0.
Yeah, the additive
Yeah.
identity. Similarly, if bi is equal to 0 for every place over here, it is the additive identity.
Yes.
Yeah, so this number A and this number, which contains 1 at the last place and 0 everywhere else, evaluates to 0.
0.
They sum. And what is another way of saying that two numbers add to 0? That one is the negative of the other.
Yeah.
Right?
Yes.
Which is what is written over here. This number, that is a, is equal to the negative of the number over here, which is 1. 1 times 2 to the 0 and 0 everywhere else.
Oh. Oh. Nice.
Yeah, makes sense?
Yes, sir. Thank you.
It, yeah. Okay, so where were we? Oh yeah, I was explaining division, right? Yeah. So one way of interpreting the fact that we carry down a 0 from top to over here, for example, when we get the remainder 6 and we carry down a 0 over here, is to say that 6 is being divided by 1 over 10. Okay? Similarly, if we subtract 1 from 15, if we subtract 15 from 1, we get minus 14, and we'll have to divide it by 7 because we are in Q7. We get minus 2. Now one might ask, why did this 15 come over here? So the way to check that would be 7 times 1 is 7, and subtracting 7 from 20 gives us 13, which is too big. Similarly, we find out multiples of 3 in Q7 and we subtract them. Now the 3 times 5 is 1 mod 7, and 1 minus 15 gives 14. Right? Now to find out the next term, we have 3 times something should have the same remainder as minus 2 when considering mod 7. What holds true for that? 3 times 4 is 12, which is 5 mod 7, which is same as minus 2 mod 7. Thus we put a 4 over here. 3 times 4 is 12, subtract 12 from 2, we get minus 14 again. Minus 14 when divided by 7 gives us minus 2. And this repeats on and on because we have the minus 2 over here, minus 2 over here, minus 2 over here. I want to ask if everybody is sure they understand about this. I mean, how this 15 came about and how this minus 14 became a minus 2. Do people understand that? Oh, right. Okay. Will someone speak up? Uh-huh. Firstly, am I audible?
Yeah,
Yes,
yeah,
sir.
you are, you are.
Okay, and will any of our limit participants speak up and tell if they understand this or not?
I would like if you please repeat.
Okay, I'll repeat it once again. So the first part is to understand how this minus 14 becomes a minus 2. This is because we divided by 7 because we are in Q7. Because we replaced this 1 over 10 with 7 in Q7, right? P7 is a prime and we are putting 7 over here. And similarly, we're going to replace division of anything with 1 over 10 with anything over 7, right? So this is the first piece to understanding it, how minus 14 becomes a minus 2. The second piece of understanding is to see why this minus 15, why we subtracted 15 from this place. Uh-huh. Hands up. Yeah. The equation that we had was 1 minus 3a is congruent to 0 mod 7 mod 7. Okay, and what might be a solution to this? Will someone like to speak up? Okay, let me try to list them.
5.
Okay, so now you understand why there's a 5 over here.
Yes, yes. Now I understand.
Right? Because the only coefficients that are allowed are the usual 0, 1, 2, and so on till 6. Anything else cannot come over there. And we tried out all the possible coefficients and 5 works. Okay, now we're going to check what happens to 1 over 343 in Q90. Let's see what happens. So I would like you people to solve this one over here. What do you think is the first step to solving this? We need to find out the question is we need to find out the expansion of 1 over 343 in Q19. So the equation that we need to solve is 343 times A is congruent to 1 mod 19. Does that make sense to people?
Yes.
Yeah. So 343 mod 19 is equal to minus 37 mod 19 because 343 plus 37 is 380, which is a multiple of 19. And 19 times 2 is 38. So 343 times mod 19 is equal to 1 mod 19. So we were extremely lucky. 343A is congruent to 1 mod 19 is basically saying A is congruent to 1 mod 19, right?
Yes.
Okay, so we're putting a 1 over here and we subtract 343. What do we get over here? Come on, people,
Minus
speak up.
342.
Yeah, and what will we do to it? What we're supposed to do it? We divide by 19, right? Because we replaced 1 over 10 with 19 for Q19. We are in Q19. We divide minus 342 by Q19. Will someone like to tell me what that is? Take your time. This is a difficult calculation.
18.
Yeah, 18. So what do we want now? 343 times A is congruent to minus 18 mod 19, right? Where have I written it? It must be somewhere, yeah. What is minus 18 mod 19? It is 1 mod 19. So we're going to multiply it by 1 again. Yeah, yeah. 1 subtract 343 again. What do we get over here, people? Come on, people. Come on, someone speak up. What is minus 18 minus 343?
Minus 361.
Makes sense. And will we divide it by 19 again?
19.
Okay. Now this is a tricky place. We need 343 times A is congruent to 19 mod 19. Actually minus 19 mod 19. And we know 343 is congruent to 1 mod 19. So we have that A is congruent to 0 mod 19. We have a 0 over here and we subtract 343 times 0 from 19 to get minus 19 again. And we are going to divide it by 19 again to get minus 1. And now will someone like to speak up? What should be the next coefficient?
Sir, I didn't get the place where you means in the third line minus 19 you put 0 0 in below
Oh, I
that.
can do that. I can do that. What do you want over here? 343 times A is congruent to minus 19 mod 19, right?
Yeah.
And minus 19
Okay. Yeah.
0.
Yes, sir. Yes.
Yeah,
0, sir. Yes, sir.
makes sense.
This is
So would you like to tell me what happens over here? What is minus 1 mod 19 congruent to 19?
18 times 343.
Exactly, yeah. 18 times 343. Now I have already calculated that, so you don't have to, which is minus 6174. This evaluates to minus 6175, and we're going to divide it by 19 again. What does this turn out to be? Someone will have to do this. Okay, it looks like I'll have to do this.
so. It's 0, sir. It's mod 19.
Yeah, we need that to happen, right? We designed that to happen. 343 times 18 is congruent to minus 1 mod 19, right? So we need to divide 6175 over with 19 and stick a minus sign in front of the answer.
It's minus 325. Minus 325.
Okay, and what happens now? We need 343 times A is congruent to minus 325 mod 19. What would be the right A?
This is 2 mod 19.
Yeah, good.
So
This
it
is
will be
2
2
mod.
into 340.
Oh, that is tricky.
Oh,
You
minus
got the
3 to 5,
minus
right?
sign over here, right? Yeah.
Oh, so sorry. So it will be 17 times 340.
Yeah. 343 times 17, which evaluates to minus 5831. Uh, which evaluate, now we'll have to define the sum, which evaluates to 5 plus 6, 2 plus 3, 5, 8 plus 3, 11, 5 plus 1, 6. What happened over here is that we subtracted 5831 from minus 325, and because both numbers are negative, we ended up adding them. So we're going to divide 6156 with 19 again. What do you people think it turns out to be?
224.
Haha. So what equation do you think we need to solve to find out the next coefficient that is over here?
Then again 16 times 343. Because 325 was 2 mod 3. So 324 plus
Yeah, this is 1 mod
1
3,
mod 3.
but
Oh,
you
yeah.
forgot the minus
1
sign
third.
again, right? And the only coefficients allowed are from 0 to 18.
So 18.
Yeah, we get an 18 over here, and 343 times 18 was 6174. Copy that over here. Find out the difference, which comes out to be minus 6498. We're going to divide it by 19 again to find out a minus 342. So what do you people think happens over here now?
So 342 is divisible by 90.
Exactly. So we're going to subtract nothing. And the coefficient turns out to be 0. We end up copying 342 over here, and we divide it by 19. and we get a minus 18 over here. Now similar to addition in what do you call them? Real numbers. This 20 was same as the 20 over here, and the terms are going to go on repeating. After that 285714, 285714, 285714, and so on. Similarly, we have a minus 18 over here and minus 18 over here. So the terms are going to repeat. The only question is, what do you think is going to be the first term in the repetition? I mean, would someone like to tell me the answer to 1 over 343 up to say 3 units of repetition? Come on, people. Okay. Looks like nobody's brave enough. Okay, let me talk about that. This minus 18 is same as the minus 18 over here. So this segment from, let me use the pen. This segment that starts with over here and comes on till here is going to repeat again. So we'll have 343 times 1 is which will give us minus 343, and this will give us minus 361, which will again divide by 19 to get minus 19. Then again as 0, then minus 19 will become minus 1, then we'll subtract 343 times 18 from that, and we'll end up having this as our answer. Right? I mean 1 and 1, 0, 18, 17, 18 repeating on and on. Yeah, I did not show this to you. Oh yeah, you worked hard. So what happens if we had used 4 instead of 7? Would we have a solution to 1 over 3 in Q4? That is, we are answering this question over here. It is not clear why P has to be prime. Would we be able to find out 2 over 7 in Q4? Suppose we had an answer. Let it be. Consider another element in Q4, that is S is equal to 2 times 4 to the 0 plus 2 times 4 to the 1 plus 2 times 4 to the 2, and so on and on. Is this an element of Q4, the set over here? So we replaced P with 4 and we disregarded the condition that P has to be a prime. Right? Then 2 is in 0 to 4, 3, and 2 is 0 to 3 again. And this is an honest to goodness element of Q4. But clearly S square is going to be 0, because every time we're going to have to multiply at least 2 things, at least 2 coefficients, that is. And we have that S square is equal to 0, whereas S is not equal to 0. And that is truly bizarre. So we have decided to not consider it. Qk, if k is not prime, is not well behaved, so we decide to not consider it at all. Now we will show that Qp is also completion of Q in some manner. Definition. For a field k, an absolute value on k is a function such that does everybody know what is a field? People?
Have a general idea, but do not know the exact definition.
Okay, that is not really required. So the first thing is that you do not need to know the definition of field to follow what's happening over here. Secondly, a field is a set where you're allowed to do addition and multiplication and division to all elements except 0. Right? So everyone who did not know the definition of a field, would people like to tell me, is Z a field? Z, that is the integers. Is that a field?
No, bhaiya.
Oh, good. And what about N? Natural numbers.
Also not.
Okay, good. What about Q? Is Q a field?
Yes, sir.
Yeah, and that is good enough. Yeah, and now we're going to define an absolute value on a field. And the field is a place where you're allowed to add, subtract, multiply, and divide all elements except 0. You're not allowed to divide by 0. The absolute value of x is equal to 0 if and only if x is equal to 0. That is, this condition was violated for Q4. Do people think Q4 is a field? Would someone like to tell me if Q4 is a field?
I think not because S has no inverse.
Exactly, good. There is nothing that you can multiply with s to get 1 because s square is 0, and then you could multiply the same hypothetical element 2 times to get the inverse of 0, which is bizarre because 0 does not have an inverse, not an multiplication inverse, that is. Yeah. Other than that, now we have understood what is the first condition. The second condition on the function absolute value is that the absolute value of a product is the product of absolute values. And the third condition is that absolute value of a sum is less than equal to the individual absolute values, the sum of the individual absolute values. And one more thing, the absolute value is called non-Archimedean if the absolute value of x plus y satisfies this particular thing over here. That is, it is less than or equal to the maximum of the two individual absolute values. A few examples are in order: r and the usual absolute value, that is, we call it modulus. Mod of x is equal to x or minus x depending on the sign. The same for q, and the absolute value, the usual one on c, that is mod of a plus yb is equal to a squared plus b squared. The square root of a plus a squared plus b squared. Yeah. In each case, we are calling a number small if mod a is very small, right? For example, 0.1 is smaller compared to 1 because the absolute value of 0.1 is smaller than the absolute value of 1. Similarly, 1 plus I is smaller than 10 crore plus 10 crore I because the absolute value of the first is less than absolute value of the second. Instead, one can decide to call a number small if it is divisible by higher and higher powers of p. For example, 0 is a very small number, and it is divisible by p to the n for higher and higher powers of p, all powers of p, right? This notion is slightly different compared to our usual notion of numbers being small and large, but we're going to codify it in mathematics and see what happens. So a valuation is a function from z minus 0 to r such that for all natural numbers z in z minus 0, the evaluation of n is the positive integer such that n is equal to the p times the valuation of n times n prime, and p does not divide n prime. Right? So suppose n is equal to 200. What do you think is the valuation of n with respect to 5? People speak up again. What is the valuation of 200 with respect to 5? Valuation is the solution
It's
to this thing.
it's 2.
And
The
why would
2,
that be?
because like 200 is equal to 25 into 8.
And 25 is 5 squared, right?
Yeah,
Okay, this is 2. What do you think is the valuation of 200 with respect to 3?
0,
Okay. And with respect to 2?
3.
Okay. Now someone else, would they like to do the same exercise for n is equal to 2 square times 3 cube times 5 to the 5? What is the valuation of this n with respect to 5?
5, sir.
5.
Okay, thank you. With respect to 3?
3.
3.
And with respect to 2?
2.
Okay. Now we can decide to extend it. Recall that the valuation was defined in z minus 0, and we're going to extend it to q minus 0 via this equation. So supposing one might want to find out the valuation of n1 over n, what the what would that be?
Minus 3.
Makes sense, but with respect to what number? 5, 3 or 2?
5, 5, 5, 5.
Okay, good. And with respect to 3?
Minus 3.
And with respect to 2?
With respect to 1.
Okay, good enough. Now a few properties. We are going to use the valuation to construct another absolute value on Q. So we are going to prove the few properties that are required. The valuation of the product is equal to the sum of the valuations. So we're going to prove that x is equal to p to the q1 a over b and y is equal to p to the q2 a1 over b1 such that p does not divide a1 and p b1. So in this case, what do you people think is the evaluation of x? Come on, what do you think is the evaluation of x over here? This is the definition.
It's q, like q1.
Q1. Yeah. And for y, what do you think is it? With
Because
respect.
p doesn't divide a or b.
Yeah, good. And what about y? What is the
q2.
value? Okay. Now we're going to prove the proposition. The valuation of xy is the valuation of p to the q1 plus q2 and a1 over bb1, which is not divisible by p, so the valuation of xy is equal to q1 plus q2, and the valuation of x and y, as you people told, are q1 and q2 individually, so the first one holds true. We're going to prove the second one out now. The second one is that the valuation of the sum is more than equal to minimum of the valuations individually. Without loss of generality, q1 can be greater than q2, then x plus y is equal to this thing, and we find out the sum and usual natural numbers and rationals to find out this. P to the q2, p to the q1 minus q2, ab1 plus a1b over b1 b2. Would someone like to tell me how this became this?
Like valuation of x plus y is q2 because q1 minus q2 greater than 0. So the numerator isn't divisible by p because a1b isn't divisible by p.
Okay,
Similarly, b1 b2 is not divisible by p.
so does this hold
So
true?
we have, yeah, because we have vp x plus y equals q2 and min of q1 and q2 is q2.
Exactly, this makes sense. Yeah, now we're going to define an absolute value out of Vp. So the absolute value is going to be p to the negative of Vp whenever x is non-zero, and it will be 0 whenever x is equal to 0. Theorem that the absolute value that defined above is indeed an honest to goodness absolute value. The first claim is that the absolute value 0 is equivalent to saying the element is 0. So x is equal to 0 implies x is the absolute value of x with respect to p is 0. By definition, yeah, this thing over here. What about the other one? Suppose the absolute value of x is 0 and x is non-zero. What happens then? Then p to the negative valuation of x is equal to 0. And this is not possible just by usual exponents. So we have that absolute value of x is equal to 0 is equivalent to saying that x indeed itself is 0. For claim 2, that is the absolute value of a product is equal to the product of the absolute values. It is the absolute value of xy is equal to p to the negative absolute value of xy. Valuation of the oh god. The absolute value of xy is equal to p to the negative valuation of the product xy, which, as we did in prop 1, it is the sum, and the minus comes out over here and sticks on the ends, and this is exactly p to the valuation of x, p times p to the negative valuation of y, which is indeed absolute value of x and the absolute value of y. So the equality of the absolute value of the product is equal to the product of absolute values is satisfied. For the last claim, that x plus y has an absolute value less than equal to the individual absolute values, and we're going to prove something more than that. We're going to prove that the absolute value of a sum is less than equal to the maximum of the individual absolute values. Let x is equal to p to the q1 a over p and y is equal to p to the q2 a1 over b1, such that p does not divide a b a1 b1. By prop 2, the valuation of x plus y is less than equal to the minimum of the individual absolute values. So minus times the absolute value is less than equal to minus my minimum of upx and upy, and this goes under this and this goes under this. We get this over here. Now note that the sum of the absolute values with respect to p, that is x plus y, evaluates to this. This is the same thing as we did over here, right? Coming back down, we use the product thing and break it into the parts, and note that bb1 1 over bb1 has the valuation 1. So p to the negative 1 over bb1 has the valuation 0. So p to the negative of 0 is equal to 1, and so we can ignore that. This becomes the valuation. This becomes p to the negative q2 times p to the negative valuation of this thing over here, which is less than equal to this thing over here, which is less than equal to p to the minus q2, which is equal to the maximum of the individual absolute values. Thus, not only is the function that we defined above an absolute value, it is a non-Archimedean absolute value. Another theorem, the absolute values fit together. This is Ostrowski, such that for all x belonging to non-zero rational numbers, the usual absolute value times the product of the absolute values where p is prime is equal to 1. We're not going to prove this today, but this sure does look good. We know that Q is not complete with respect to QP, and the completion of QP is R. Okay, to bring more nuance into the discussion, R is the completion of Q with respect to the usual metric, that is mod of x is equal to x or minus x depending on the sign. It turns out that QP is the completion of Q with respect to the new absolute value that we defined above. We're going to prove one side of this thing, one side of the equivalence between our old QP and our new QP, where the new QP is defined to be the set of equivalence classes of Cauchy sequences. That is, xn is Cauchy, and for all two sequences xn and xn prime, if the limit of their difference in the p-adic absolute value goes to 0, then they are said to be equivalent. It is easy to see that the old QP is contained in the new QP, which we have called QPR. That A belongs to old QP and A is equal to summation I equals z0 to infinity AI p to the I. And then we define an to be the nth partial sum of the whole series. Then for all natural numbers n and for all m2 more than m1, if we set capital N more than capital N of n is equal to n plus 1, then am1 minus am2 with respect to the p-adic absolute value is equal to this thing over here, which is equal to this thing over here. Would someone like to tell me why is that true?
So we have assumed M2 greater than M1.
Yeah.
So we are means the way we have defined AMI and means
Uh-huh.
AN. So the sequence will have truncated, right, at the point
Yeah.
M1. That's why this works.
Yeah.
And we are expanding base P. So
Okay, so what you want to say is that we can take p to the m1 common out of that sum and it won't, I mean,
yes,
disturb the terms of the sequence.
yes.
And then the coefficient of p to the m1 would be anything. It might even be 0, but if
It
it is
won't
not
divide
0,
P, right? It won't
yeah.
divide P anymore because it's the highest power there.
Okay,
That's
good. So it becomes p to the negative valuation of this thing, which is m1, which is 1 over p to the m1, which is less than equal to 2 to the m1, because 2 is the smallest prime, and which is less than equal to 1 over n1, because this is true and n belongs to n, so n is more than equal to 1. This means m1 is more than equal to 2, so we have the 2 to the n is less than equal to, oh god, the other side, more than equal to, more than equal to n, and we assume that m2 is more than m1, so that this is less than equal to n plus 1. Thus, we have proved that an is a Cauchy sequence. To reiterate, we had this whole set over here that we had defined above, this thing, and elements of this, when we consider them as partial sums, are Cauchy sequences. Thus, it must be represented by some representative in QP hat. It is this thing over here. So all in all, we are almost beyond our time limit, and there's one more comment that I'd like to make. So there was some kind dude who said that God gave us the integers and all else is the work of man. Now today we started from the empty set, that is nothing, and made a little something out of it. I hope you liked playing God. Thank you for listening to me today.
Yeah, thank you so much, Pranav sir. And your talk is really wonderful. Okay, so now it's a question time.
Okay.
So there are not much questions. A question comes from Ayan Ghosh. What do you mean by well defined?
Okay, I suppose you're talking about this over here, right? Ayan, will you please speak up?
I just didn't get what does value. Yeah.
Okay, so hypothetically speaking, it would have been possible that if I made the wrong definition, then m the sum of two elements might actually depend on the representative, because as you might recall that these are the equivalence classes of n cross n modulo the equivalence relation, right?
Yeah.
Elements of Z, yeah.
Means are we
And
like proving that a plus b equal to b plus a? Something like that.
no, that comes up after that.
Sorry.
First, we need to prove that the operation is indeed well defined,
Okay.
because it is hypothetically it is possible that if you take, I mean, you agree that 1 comma n and n comma n denote the same equivalence class, right?
Yeah, of course, of course.
Yeah. So hypothetically, if I had defined addition of two elements of n cross n modulo tilde as the sum of the first and the second, what do you call them, coordinates, right?
Yes.
Then it would actually depend on which representative I choose to add,
Hmm.
right?
Yes.
Sometimes it will be 2, sometimes it will be 4, sometimes it will be 8 or something. It could be anything, right?
Anything, yeah.
Any even number. And that would be a bad definition for addition even if it did work.
Hmm.
Yeah?
It would not means work for all numbers.
Yeah. It won't actually work. Yeah?
So
There is
we are
another
like
question. Okay, okay.
proving
Yeah,
Continue.
that it's the thing is related to that
Uh-huh.
is a, say a tilde b and c tilde d. So a plus c is b plus d. So that
Yeah.
makes it yeah.
Yeah. Because
It
it
is
is
unique.
possible that these two individual terms in n cross n might add up to different things.
Oh, yes. But it
Right?
doesn't means.
Yeah. But because we defined it in a clever manner, that
Hmm,
does not happen.
doesn't. Okay, sir.
Thank you.
Thank you.
okay, so next
Good
question
question.
comes from
Uh-huh.
Vivek Kumar Singh.
Uh-huh.
Shouldn't we also prove that multiplication is well defined?
Absolutely, you should. I mean, but then this talk would be very boring. I mean, I'll have to prove well-defined and associative and commutative for addition in N, then separately for addition in Z, then separately for addition in Q, then separately for addition in R, then separately for addition in, what do you call them, p-adics, and then you'd probably go to sleep. But you sure should do that.
Yeah, next, how did we define the valuation of elements of QP?
Oh, wow. That is a good question.
Yeah, the question comes from Ojas Mittal.
Let me reach the right place. So the question is over here, right? Note that we started at z minus 0, we extended to q minus 0. Uh, we never really defined the evaluation on qp, and over here we never really defined the valuation for elements of, I mean, we never really defined the absolute value for elements of qp. Why do you think would that be true?
Yeah,
Ojas, yeah,
Ojas.
you can unmute your.
Yeah, I was asking like we defined the valuation of like natural numbers and a
Uh-huh.
rational number. Did we also define the valuation of elements of QP?
No. I specifically told you, right? We did not do that.
Okay,
Even the absolute value is not defined for elements of QP, right? this particular absolute value is defined only on elements of Q.
Okay, so like
Yeah.
when we
The
say
question I am asking you is that how would you extend it to QP?
okay,
Let me help you. Let me help you. Let me help you.
so
What properties did we prove for this absolute value? This we would like this to hold in QP here, right?
yes,
We would like this to hold in QP, right?
yes,
And we would like this to hold in QP, and we would like this to hold in QP, right?
yeah.
Are these three properties enough to find out the valuation?
Uh,
Let me
like
help you.
how do we
Let
use
me
these
help you.
properties to find the valuation?
Yeah, this all these properties hold for Q only, right? We discussed
Yeah,
that earlier, and hypothetically, this is an element of QP, right?
uh, yes.
And because we did subtraction, we didn't really have to, I mean, mess around with the notion of absolute value, this absolute value in QP, right?
Uh,
Because this
uh,
again turned out to be a what do you call them, rational number, and we defined the absolute value for these things.
yeah.
And the key to defining the absolute value in QP is how we come from this to this. Would you like to explain me how this happened?
No, that's fine, but this is still like
This is on
this is
Q,
still
right? It is true that this is on Q. But would you like to tell me how this happened?
uh, this is because like uh, the VP of this element in Q is p power m1 because like all AIs are rational numbers which
No,
have
no, no, no,
definite
no, no. Be careful,
denominator.
be careful. All AIs are elements of n from 0 to p minus 1. They are indeed rational, but that is missing the
Oh,
point.
okay, yeah, okay.
Yeah?
So uh,
So this
wait,
is,
like do we need AIs to not equal zero also because
yeah, yeah,
otherwise
yeah, yeah. That would be true, but I mean, subtracting 0 and proving things is boring and so. And
okay.
yeah, so for your convenience, you can assume that these AIs are all non-zero, and then explain how we go from this valuation to this thing, e to the minus n1. How did that happen?
Uh, that is because like VP of this element, which is a natural number, summation I is equal to m1 to m2 minus 1 ai p power I. This is a natural number, and VP of this number is m1 because the other terms have like if we factor out p power m1 and
Uh-huh.
uh, denote the other side as ai p power I minus m1 from
Uh,
m1 to m2 minus m2
uh,
minus 1, then that thing is not divisible by p.
exactly. And hypothetically speaking, even if that thing was going on and on till infinity, would that be divisible by p?
Okay, so even if it is to infinity, okay, so do we define it in this way like the first non-zero ai its
That is indeed
power
the correct way
and
to do
p
that.
power.
That is indeed the correct way to do that.
Okay,
Well,
Thank you.
well done. Any other questions?
Anyone else have any questions or doubt? Please raise your hand or just unmute yourself and ask. Yeah, there is one more question
Uh-huh.
from Shivanti. Can you give some good applications of valuation?
Okay. Do you mean questions? Will you please speak up, whoever asked the question? I don't understand what you mean by applications.
I mean
I
Shivanti,
can tell you.
concepts where we
Okay,
can
okay.
apply this concept to make it easier.
Uh, so the thing is that valuation that I have defined, it is really a specific definition for something that happens in more general settings. Okay, so there is this thing you can search on the internet. Things are called rings, and you can define a valuation on a ring, and then you can do all kinds of stuff with that. And what I have defined over here is exactly the definition of valuation of a ring, but the ring that I have chosen is Q. Okay, so what do people do with valuations? The thing that I have done with valuations is to solve questions related to valuations. So there's that. But other than that, I'm sure people must have proven things with it. I don't know. I can tell you what people do with QP. Um, would that be good enough? Shivanti, would you like me to tell you what happens when people do things with QP?
Okay, sir.
Ah, so the first thing to note that is we have the set R, right? People do calculus on R. Similarly, people do calculus on QP also. And by proving calculus, I mean, by proving things and doing calculations on QP and putting a few other things in together, some do what do you call it?
Sir,
Fermat.
like,
Yeah, yeah.
do we have notions of limit,
Yeah,
differentiation,
yeah,
and
yeah, yeah, yeah. That is true.
continuity?
Yeah, yeah, yeah. That does happen. In QP,
QP.
you're talking about, right?
Yes, yes.
Yeah. So after, I mean, defining QP and becoming comfortable, you define modular forms in QP. And when you are struggling with modular forms in QP, you can become, what do you call him, Andrew Wiles, and prove Fermat's last theorem with p-adic integers and things like this. So that is one of the things people do with QP. Does that answer your question, Shivanti? Is this good enough?
Yes, sir. Thanks.
Aha, welcome.
anyone else?
Um,
Okay, if there is no more questions, then we'll stop here. Thank you, Pranavda, once again, and thank you to all the participants.
And also, I wanted to mention that many of you have not entered your name in the sorry, roll number in the name. So kindly do that in the next. This time we have allowed. From next time, I will not. Be careful with that. Okay, then. I'm ending the meeting. Bye.